Hello. Well, as always, when I remember, I start my lesson by setting up my stopwatch. While I'm doing that, my name is Sosale Mahana. I'm a teacher of mathematics. I've taught A-level maths for a long time, and I'm using these lessons to go over various topics in A-level pure maths to help you revise and prepare for the exam, and also to go over what you have been taught by your teachers in school. So we were in topic 6, differentiation. I had told you last time that I'll spend a couple of more lessons on this, and so today we will do this. I think this has been discontinued, if I'm correct, but I am not very familiar with the AQA syllabus, and so I would rather do it just in case. It's in one of the syllabi. See, when we define dy by dx, we said dy by dx is limit delta x tending to 0 of delta y by delta x. That means it's the rate of change of y with respect to x for very small changes in x. So what we're trying to do is, if for example the volume is related to the radius, if there's a very small percentage change in the radius, what might be the percentage change in volume? That's what, remember we did last time related rates. This time we're doing small changes, wherein how is a very small change in x, how is it going to affect the change in any other variable connected to x, yeah? So, in other words, since delta x is small, I can conclude from here dy by dx is approximately delta y by delta x, where delta y is the change in y, delta x is the change in x. So, change in y is approximately dy by dx at a particular value of a times change in x. This is the formula for small approximation. Don't confuse this with the small approximations for sine and cos. I'll take a couple of examples and then show you how to do this. Bit of a problem with this board. It doesn't rub properly, so I might have to do a bit of a doctoring. Let me see if I can do a bit of doctoring. Yeah. I don't know, suddenly we used a chemical to wipe this and the whole thing became a mess. I wonder what the chemical contained. It became a big mess. So, for example, let's say you're told that the radius of a sphere is increased from 4 centimeters to 4.01 centimeters. Find the approximate increase in its number 1 volume and number 2 surface area. So first and foremost, as usual, identify the variables. The variables are the radius r, the surface area A, and the volume V. So volume V equal to 4 over 3 pi r cube. So what is dV by dr? dV by dr is 4 pi r squared. So delta V by delta r is approximately 4 pi r squared. So delta V is approximately 4 pi r squared delta r. You're being told that the radius of a sphere increases from 4 to 4.01. So at r equal to 4, volume is 4 over 3 pi times 4 cube. So 256 pi over 3. Right? So the change in volume and the change in radius is 0.01. So change in volume will be 256 or 4 pi r squared. Sorry. I don't need it. I just found it. Doesn't matter. Is 4 times pi times 16 times delta r is 0.01. Whatever is the answer. 64 pi, so 0.64 pi. So if you remember, it depends upon what the radius is at a particular moment. So the change depends upon what the value of the radius is. Now let's come to the other one. Am I correct? Yeah. Delta V is 4 pi r squared delta r. That's correct. dy by dx at x equal to a. This will be at r equal to 4. At r equal to 4. So in fact, this is a superfluous information. I just did it just to see where it leads to. Okay. Let's find the change in surface area. Yeah. When the radius changes from 4 to 4.01. Okay. I'll have to rub this, otherwise I want more smudging. Okay. So now surface area is 4 pi r squared. So dA by dr is 8 pi r. Always replace dA by dr by delta. A by delta r is 8 pi r. So delta A is approximately 8 pi r delta r. You know r is 4. Delta r is 0.01. So delta A is approximately 8 pi times 4 times 0.01, which is 0.32 pi. So that's approximately centimeter squared per centimeter squared. So that will be the approximate increase in the volume. Good. This closes. Oh, my wiping towel has fallen off and an old man has to bend. Hope you don't mind. Oops! At last. So what I'll do is I'll have to wipe with a wet towel and then with a dry towel. Amazing. That's a dry towel. That's a wet towel. I get confused what is what. I'll keep it a bit wetter as well. I'll make it a bit wetter so that it's easier. I hope this works. It does. Of course, we'll know the effect tomorrow morning when the water dries up. You might find a cracked board tomorrow. So to avoid that, I'll wipe it now only so that we have a easier, cleaner board without cracks for the next lesson. All right. Remember, the period of a pendulum is 2 pi root L over G. Those who do physics know it. So T is 2 pi root L over G. Okay. Or can you say T squared is 4 pi squared L over G, or L equal to G over 4 pi squared T squared. So can I call L as AT squared? So that's what I'm going to use. So the length of a pendulum and its period, that is time taken for one complete swing. We start from here, go there, comes back. One swing, or related by the equation. I'm just making up these questions by the equation L equal to the length L of a pendulum and the period T, or related by L equal to AT squared. So what they're asking you to find is, if the length is increased by 5%, find the approximate increase in the period. Well, so I know L is AT squared where A is a constant. So dL by dt is 2AT. So therefore, delta L by delta T is 2AT. So delta L is approximately equal to 2AT delta T. You need to find what is delta T. You're being given L is increased from whatever was its length by about 5%. So therefore, delta L would be 5% of L. Delta L is 5% of L, which is 5 over 100 times L, or 0.05 L. Yeah? So that I'll put there. 0.05 L is approximately equal to 2AT delta T. So what is the increase? So delta T is 0.05 L over 2AT. But I need a percentage because I don't know what the value of T. So what can I substitute L as? That is 0.05. What is L? Is AT squared divided by 2AT. A and A goes, T and T goes. So delta T is approximately 0.025 T. So what the percentage increase? You can do it directly, 2.5%. But if you want to do it, you could say delta T over T times 100. So that's approximately the 0.025 T divided by T times 100, which is 2.5%. That means if you increase the length of the pendulum by 5%, the time taken for an oscillation will increase approximately by 2.5%. This is what, these days of course we have digital clocks. In your grandfather's time and my younger days, we had, every house had this pendulum clock. Yeah, and I still remember in summer, because it was a metal piece and with a small disc at the bottom, I myself would see that the length would increase. So if the length increased, then you see the period would increase. So we had to, somewhere in the month of April, in the hottest period, we had to shorten the length. And of course, we didn't know how much to shorten. I hadn't done calculus by then. So we would just trial and shorten one day and see in 24 hours what's happening. Because, we had the wrist watches, which once you wind, they're not affected by the temperature. Because remember, heat expands solids and cold contracts them. So during the heat, the metal rod would expand a bit. It was not much in the summer. I don't know whether you people have observed a railway track. These days, of course, it's not there because some scientists found out, when you, this is just out of interest, nothing to do with maths, just a bit of general knowledge. When you lay a railway track, you put two tracks, you always leave a gap in between. The reason is, if you don't leave a gap in between, what will happen will be, in the summer, they tend to expand because they're exposed to sun for about 12 hours, 13 hours a day. Then they expand and the track will bend and the train will derail and fall. So they have to leave a gap to account for that expansion. That's so in traditional trains, as it went faster, you would make a clacking noise as it went over. But these days, somebody found a particular alloy to fill the gap. That alloy expands and contracts depending upon the heat, so the track remains smooth. That's these days. Whereas if your granddad is alive or grandmom is alive, talk to them when they used to go during the steam train age on the tracks. Oh, the amount of noise you would get if the windows were open, especially in the summer when it was very warm. When the windows were kept open, oh, the clamoring was so much. Oh my God. Just can't. I'll just do one more example. Find, using small approximations, square root of 16.04. No, 16.05. Right? So we're dealing with square root of a number. So you start with the function y is square root of x equal to 16, delta x equal to 0.05, y is equal to 4, delta y equals 1. Once you find it, you can do y plus delta y. What's dy by dx? Dy by dx is, this is x power half, gives you half x power minus half, write it as 1 over 2 root x. So delta y is approximately 1 over 2 root x delta x. Put the values. So delta y is approximately 1 over 2 times 4 times 0.05. So approximately 0.005 divided by 8. 8 ones are 8. 8 6 are 48. 220. 8 2 are 16. 0.00625. So square root of 16.05 is approximately 4.00625. How good is this approximation? Shall we check? How good is it? We're looking at square root of 16.05. 4.006245. 4.0. So it's almost approximate to, when you round it, it is 1, 2, 3, 4, fifth decimal place. So they agree when you round it to 5 decimal places. That's pretty powerful, isn't it? Very interesting. So that concludes small changes. I will see in the next lesson. I want to just I'm thinking as to what I should do. Perhaps what I'll do is today is Saturday. I mean, recording has got nothing to do with the time when we upload. So what I'm looking at doing is over the weekend, look, by teaching you, I end up having weekend homework. I still remember, if you know anybody from St. Edmund's College, UK, who did further maths when I was teaching further maths, or my students back from Kenya, Oshwal High School or Jamhuri High School, not Jamhuri, yeah, Jamhuri High School or Premier Academy, where I was teaching. If you know anybody in Kenya who was taught by me from between 1978 and 2003, or at St. Edmund's College 2004 to 2019, ask them about the homework I used to give. My students used to curse me for giving them so much homework. So in fact, for the maths, students would get a lot of homework. Now it's payback time. Because I have to teach you maths now, because I took it on myself to do it, I have to now sit. What I want to do is, I've taught you so much of differentiation. So I want to do a plenary or a revision session wherein I take a number, 2-3 lessons, taking a number of questions from, not from past papers, but from my memory. I can pick up a question and then make my own questions over the weekend and then solve them for you as a sort of a revision on differentiation. I think I'll do that, okay? So I'll see you next time. Have a nice day. Bye-bye. Hello. I want to take this opportunity to propose a vote of thanks. I would like to thank Vivid Innovations Private Limited and Commerce Forum for so generously giving up their studio and the facilities and the services of their technicians to record all these videos for free. I think that needs to be acknowledged and appreciated. Thank you very much. And my special thanks to Mr. Nitin Mahadevappa, Mr. Nishant Guruswamy, and Mr. Sadan Kumar DN for all their help and assistance in getting these videos ready, uploaded and launched. Thank you very much.